Hello and welcome to week 11 of the NPTEL MA106 Category Theory course. This week we have covered a lot of. By the way, I am Shubhajit Das. I am a PhD student at the Department of Mathematics at IISc. And this week, in week 11, the main topics of concern are the following. So I'll just write down the topics and we'll see what things we will do. So just a minute. Okay, so the main content of this week was homological algebra, and this week probably one of the most important things that you learned was the notion of a projective object in an abelian category, and in fact in any category. So using projective objects, the main purpose of working with projective injective objects is so as to talk about certain nice functors associated to a given functor, which are called derived functors. So there is the notion of a left derived functor for a right exact functor, and there is a notion of a right derived functor for a left exact functor. The interesting thing about the category of topological spaces that you learned is, about the category of chain complexes that you learned this week is that chain complexes themselves support a homotopy theory. So you can talk about a notion of homotopy of maps of chain complexes, and you can construct a homotopy category of chain complexes as well. So in many ways the category of chain complexes is very similar to the category of topological spaces, even though they are not exactly the same. And I believe you also learned something called simplicial sets this week, right? Was some content on simplicial sets covered this week?
I think so.
Okay, so simplicial sets, topological spaces again are very similar objects. Associated to every topological space, there is a simplicial set called the singular simplicial set, and associated to every simplicial set there is a topological space, and in fact you get an adjunction between the category of topological spaces and the category of simplicial sets, which is not just an adjunction, so to say. It has further properties. So even though the two categories are not equivalent, they are related by an adjunction, which actually is something called a Quillian equivalence in the sense of homotopy theory. We won't get into the details of that, but the idea is very simple, and it's only one, that topological spaces and simplicial sets are supposed to behave in the same way, and in fact simplicial sets are sort of combinatorial models for topological spaces. Simplicial sets are used in other contexts as well, but you can think of them as a more tractable. So a simplicial set is a more tractable version of a topological space. That's all. There are more algebraic things that you can that are available that you can do with simplicial sets, which perhaps would not have been possible for just topological spaces. In fact, with every so there is some notion of something called an infinity category, which allows objects, morphisms between morphisms, etc., and so on. You keep on doing this. So you have objects which you think of as zero-dimensional things in that category, in that infinity category. You have morphisms which are one-dimensional in the sense that they are directed edges. You have two-dimensional morphisms which you can think of as areas from one-dimensional morphism to another one-dimensional morphism. You have three-dimensional morphisms, spaces, etc., and you keep on doing this. So, and it goes until infinity. So this is roughly the notion of an infinity category. There are various different models to study them, and the main purpose of introducing infinity categories is to talk about homotopy theory. So all these are pretty related, notions. The interesting thing is that to every associated to every category there is, I mean, to every category there is an associated, or okay, these are not precise statements, but in a rough way you can say that to every category there is an associated infinity category, and the category of topological spaces and the category of simplicial sets, I mean, their infinity categories are the same, roughly speaking,
Is
even though the
that
two
called
categories
nerve
are.
of the category?
Sorry.
Is that called nerve of a category?
Yes, nerve of a category is a simplicial set. So I can give some ideas on this, even though this will not be not from the content of this week, but the idea is pretty simple. So so first of all, what is so okay, let me quickly give you some information about what we will be doing this week. I mean, you already know, but still, let us fix some notation. So in this week we'll see, or we saw, some homological algebra. I'll just list down the stuff that we saw. So there is a notion of so long exact sequence of homology associated to a short exact sequence of chain complexes. We saw this. What else? Homotopy category of topology, I mean, sorry, chain complexes. So there is a notion of homotopy in the category of chain complexes, just as you can talk about a homotopy of maps between categories. I mean, of maps of topological spaces. Similarly, you can talk about homotopy of chain maps, and that allows you to construct homotopy category. Then you also probably saw derived category. I mean, some things need to be said before that. So you also saw the important notion of projective objects, and the main purpose for introducing them was to introduce projective resolutions in homological, which form like the basis of homological algebra. So the homotopy category is constructed in the obvious way. I mean, you take a category. Okay, so can you take okay, so before we get to homotopy category, a very simple question: is there a notion of a quotient category in category theory? Just as we can talk about quotient groups, etc. Do you know some notion of a quotient?
Yes.
Can you explain it in details? Can you explain?
Sorry, I can't.
Yeah, can you explain the notion of homotopy? I mean, of a quotient category. Can you hear me? You can hear me, right?
Yes, yes.
Yeah. So do we? Can we? I mean, can we? Can you give me the precise notion of quotient category of a category, or what is the idea roughly?
Yeah, so if we consider a equivalence relation, which is uh, which behaves well under compositions, I think it's called congruence,
Yes.
and then we can quotient the Hom sets.
Okay. So the equivalence relation is on the Hom sets of the category.
Yes, Hom sets on the category.
Yeah. So we can take a quotient we can take a quotient of the Hom sets by that equivalence relation, which which is referred to as rather a quotient of the category itself, and that is your idea of a quotient category. So there should be a universal property here as well, right, for quotient categories.
Yes.
So what can you tell me? So what kind of universal property should we have? Just as we have universal property of quotient of groups or quotient of topological spaces, we should also have the notion of quotient. I mean, we should also have a universal property for quotients of categories. So what should it be? So
what I think for that we need functors, right?
yes, correct.
So if F is a functor between two categories A and B,
Yeah.
and if we have equivalence relation in A,
Okay.
I mean Hom sets of A, such
Okay.
that if such that two morphisms are related if and only if their images are equal.
Okay.
And then this functor uh, will factor through the quotient category.
Um, yeah, okay, fine. Yeah, that's the universal property. So let's say R is your equivalence relation on A. So you're correct. I mean, the idea is you take a category A and take an equivalence relation on A, and in fact you can say just a relation. When you take a quotient, it's understood that that relation will generate an equivalence relation, and so the quotient category is A over R. Let's say A over R, where R is an equivalence relation. You have a canonical functor, let's say pi, from A to A over R, and this is universal among all functors. With the property that pi, I mean, if f is R related to G, implies pi f is pi G, right? So this is universal among all functors with this property. So in the sense that if you take an arbitrary functor A to B, f, let's say, such that f is R, whenever f is R related to G, you have ff is equal to fg, then f factors uniquely through pi as follows. So A to B, f, you have pi, I mean A mod R here, you have pi here, and from A mod R to B you get a functor, let's say f hat, such that this diagram commutes. And I mean, if moreover, if f is thought of as identity on object, I mean, if our functor f is I shouldn't say it in this way, I should rather say that the functor f hat can actually be defined in a way that its effect on objects is the same as the effect of f, the action of f on objects of A. So the objects of A over R are still the same as the objects of A. You just change the Hom sets. You just take a quotient of the Hom sets. That's all. Yeah. So this is the universal property of quotient categories, and hence is enough. I mean, can also be thought of as the definition of quotients. So the idea is pretty simple now. You have some category, the category of chain complexes. You have a notion of homotopy, which actually forms an equivalence relation, and you can take a quotient of your category by with respect to homotopy, which is now called the homotopy category of chain complexes, and as far as I remember is denoted as k of so k of A. So if A is your abelian category, if you take ch of A, the category of chain complexes, so from this to this you have a quotient functor. And how do you get the derived category? You use the idea of localization. So you localize your Ka at the quasi isomorphisms, and that is how you arrive at the derived category. What is the notation used for derived category?
D.
D. Correct. DA. So this is the construction of derived category. And what else was covered? Okay. Okay, so you also, so in the next lecture you learnt about the idea of weak factorization systems. So I'll introduce a small notation which will be relevant towards to solving our problems. Yeah, so what is the purpose of a factorization system? The main purpose of a factorization system is to factorize morphisms. Okay, so so for example, in abelian categories, we know there is every morphism can be factored as a epimorphism followed by a monomorphism. So if you look at the class of all APs together with the class of all monos for an abelian category, this forms a factorization system. There are other properties which we haven't mentioned, or probably which was mentioned in the lectures. The idea is that APs and monos form a factorization system for abelian categories. So the lectures introduce the notion of a weak factorization system. And okay, so can you tell me what is the definition of a weak factorization system? Can you recall? Can you recall the idea of a weak factorization system?
No, I forgot actually.
Okay, no worries. Okay. So something called lifting properties was introduced, right? So okay, so let's write it nicely. Okay, so let I and G, I and P is, yeah, I and P be morphisms in a category C. A lifting problem for I and P. Let's write things in this way. This is not exactly how it is written. A lifting problem for I and P is square of this form, which looks like this. So you have I here and you have P here. This is some arrow in your category, let's say F. This is some arrow in your category, let's say G, which is commutative. It's just a square which is commutative. Now, looking at a commutative square, what you are rather tempted to is sort of break it up into triangles, and that is what a solution of a lifting problem means. So a solution of this lifting problem, also called a lift, is a diagonal. So it's a morphism which sort of fills up the entire diagram. So it's a diagonal morphism as follows. So this diagonal morphism is called the lift, or the solution of the lifting problem. It's called a lift or a solution of the lifting problem. Let's say this is H, such that the two triangles commute. Now let's this is where this is the notation that I wanted to introduce. So if this happens for every F and G, so in other words, if for every arrow F and for every arrow G in your category, if this lifting problem has a solution, then I'll say that I has the left lifting property against P or with respect to P, and P has the right lifting property against I or with respect to I. So if the lifting problem, so if the lifting problem above has a solution, we are not asking for uniqueness of the diagonal morphism, we are just asking for existence. So if it has a solution for every F and G arbitrary arrows in the category, then I is said to have the left lifting property. So I mean, instead of writing it in details, in full, I'll just use abbreviation. So it has the LLP with respect to, because you have already seen this during the lectures. So it's said to have the LLP with respect to P, and P is said to have obviously the RLP with respect to I. And sometimes this is denoted by using the following notation. So this is, so if I has the left lifting property with respect to P, in other words, whenever you take a commutative square like this for arbitrary arrows F and G, if this commutative square can be completed by using a diagonal morphism as follows, that is if it has a solution for every F and G, then I is said to have the left lifting property with respect to P. So if I has a left lifting property with respect to P, this is denoted by I. So you use a box and a diagonal like this, P. This is how it is denoted. So this is not some expression, it's just a statement. It has a truth value. It means that whenever you write this, it means that I has a left lifting property with respect to P, or equivalently P has the right lifting property with respect to I. And moreover, if for every F and G so we are still talking with whatever we are saying is always in the context of this commutative square. So if for every F and G the morphism H which exists, because the morphism H exists and is unique, exists or rather let's write it like this: if for every F and G a unique solution or lift exists, H exists for the lifting problem, then I is said to be orthogonal to P, or sometimes also said as I is left orthogonal to P, P is right orthogonal to I. So whenever you ask for uniqueness in literature, it's referred to as orthogonality. But we won't be concerned with orthogonality, we'll only be concerned with existence of solutions. That is, we'll only be concerned with this notation throughout our problems. And why were we talking about lifting properties? So that we could introduce weak factorization systems. So what is actually a weak factorization system? So again, this has many different definitions rather. So we'll stick to one of them. I am not exactly sure what definition was covered in the lectures, but let's just stick to this. So a weak factorization system So when I say different definitions, in most cases those are equivalent. So a weak factorization system on a category or for a category or over a category, etc., on a category C is a pair L comma R, let's say. What notation was used? Was it EM or LR?
Yes, EM.
Okay, EM is a pair EM of classes of morphisms and sometimes instead of taking classes of morphisms you take subcategories. So the point is that, and whenever I say subcategory I mean some subcollection which is closed under compositions and isomorphisms. But the interesting thing is you don't need to assume subcategories actually. I mean, with respect to some properties, you can, taking some properties, you can actually prove that those will be subcategories. So, how should I write it? Let's just stick with classes of morphism.
Is it a subcategory of the arrow category?
Subcategory of what? Subcategory. Sorry, I couldn't.
Arrow category.
Yes, subcategory of the arrow category. You're correct. Yeah, I should have mentioned it. It's whenever I say classes of morphisms, yeah. So it's a subcategory of the arrow category, which is closed under isomorphisms and compositions. But let's keep things simple. Let's just only take classes of morphisms. So it's a pair of classes of morphisms such that of C such that firstly every morphism in C can be factored as a morphism in E followed by a morphism in M. Secondly, E is the class of morphisms, or let's write it in mathematical terms. This class E, sorry, I should put this on chart. Yeah, E is exactly equal to, so we'll use this notation in our problems as well. So better I write it already. So E is equal to this box with diagonal M. So what does this mean? This means, what does this notation mean? This means that this is the class of all morphisms F in C such that F has a left lifting property against every morphism in M for all M in M. Okay. So you take any class of arrows in your category M, and I define this notation, I define this operator, something called this. So I define this operator. So what does this operator actually do? In other words, what does this mean? So suppose M is any class of morphisms. So this notation means that you are taking the class of all morphisms in your category which have the left lifting property against every morphism in M. Okay, that is what was written here. F has a left lifting property against every morphism in M. So what does this entire line say actually? What does this say? This says that E is exactly the class of morphisms which have the left lifting property against every morphism in M. Dually, you also want that M should be, and now this notation is understood. So we have introduced one other notation or one other operator, which is this. So what does this mean? This means this is exactly the class of all those morphisms G in C such that E has a left lifting property against G, or rather G has the right lifting property against E for every morphism E in E. Okay. So what do these two lines say, or these two statements exactly say? That E, the class E is exactly the class of those morphisms which have the left lifting property against every morphism in M, and M is exactly the class of all those morphisms of E which have the right lifting property against every morphism in E. Okay. And as I mentioned, sometimes E and M are taken to be subcategories. You can avoid that actually. You can prove a lot of things from this only, this itself. But just for the sake of completion, let's just write those things in detail. So I'll just mention what other things that we need. So, or rather, you can prove some of this actually. Okay. The point. So what I'm trying to say is, whenever you say a weak factorization system, this is what it means: a class of morphism, a pair of classes of morphisms satisfying these two properties is called a weak factorization system. And from this, you can actually prove two further things. So E and M, these are sort of redundant assumptions. E and M are closed under compositions. E and M are closed under isomorphisms. So E and M are in particular subcategories of your category C actually. Yeah, E and M. I'm sorry, I think I made a mistake when I said that E and M should be subcategories of arrow category. E and M are supposed to be subcategories of your category. So they should be thought of as arrows in a category, not objects in some category. If I were to think of them as objects, I would have mentioned arrow categories. So E and M are subcategories of your original category, as far as I remember. But anyways, that is the reason I don't want to bring subcategories into the picture. Let's just so these are the explicit properties that you would want. Okay, saying that E and M are subcategories of arrow category would have more implications actually, which is why I suspect that is not true. E and M should be subcategories of. By the way, how was? Do you remember whether he talked about subcategories or just classes of morphisms in the lectures?
Yeah, he said these are subcategories, but he didn't.
I see. So I believe those are they are
which.
just subcategories of your category. Okay. So when I say sub,
Yeah,
so what, by the way, what is just a subcategory? A subcategory is a category whose class of objects is a subclass of the original category, whose class of morphism is a subclass, and which is closed under all the operations of your category, which is closed under domain, codomain, composition, identities, etc. I mean, not etc. That is all. These are things that you need. So it's a subcategory. It's a category which is. It's a category with respect to the restricted operations. That's all. That is what a subcategory exactly is. In other words, you have some. In other words, the inclusion assignment from this subcategory to your big category is actually a functor. That's all. So we'll just stick with classes of morphisms, keeping in mind that these things can also hold or actually can be proved. And you can prove a lot of other things. For example, so this left lifting property and right lifting property are actually very substantial and very powerful. You can prove a lot of other things. Closure under retracts in the arrow category. Closure under okay, we'll solve some of those problems. We'll get to all those things. But the point is that this is the idea of a weak factorization system. And if a weak factorization system has this property that solutions to the lifting problem are unique. In other words, if E is precisely the class of morphisms which are left orthogonal to every morphism in M, and M is precisely the class of those morphisms which are right orthogonal to every morphism in E, then this factorization system is sometimes referred to as an orthogonal factorization system. So orthogonal factorization systems are more refined versions of weak factorization systems. And sometimes whenever people say factorization system, they usually mean an orthogonal factorization system. But we'll only be concerned with weak factorization systems. What else was covered? Model structure. So we won't get into the details of what model categories are. I'm sure they have been introduced, but think of a model category as a framework for abstract homotopy theory. So you can talk about abstract homotopies in a model category. So what is actually a model category? If we just want to recall it in and not write anything, a model category is exactly a category equipped with three classes of morphisms. For the first class is called cofibrations, the second class is called weak equivalences, and the third class is called fibrations, such that some properties hold, out of which two properties are as follows. So firstly, if you take the class of all cofibrations and take the class of all weak equivalences intersected with the class of all fibrations, which are sometimes called trivial fibrations, or there's also one other term, acyclic fibrations. So cofibrations comma acyclic fibrations, this pair of classes is actually a weak factorization system for your category. Similarly, cofibrations intersected with weak equivalences, that is trivial cofibrations or acyclic cofibrations comma fibrations, this also forms a weak factorization system for your category. And there are some other properties, of course. So why all of a sudden introduce such terms? This is entirely motivated by homotopy theory in topology, and I mean in so what is roughly a fibration? So for people who know what covering spaces are, a fibration is actually something like so think of the real line, think of the circle. So what happens? You have a map from real line to the circle, which is your covering map, winding map, etc. This is an example of a fibration. So I mean okay, can you tell me if some topological I mean, did he introduce some kind of topological explanation behind those names? Because I don't exactly know if we are supposed to talk about.
No.
Okay. I mean, this is okay. Fine. Let's not get into all those things. So roughly think of, so whenever you think of cofibrations, roughly think of cofibrations as some special nicely designed monomorphisms, and think of fibrations as some special nicely designed epimorphisms. The idea of cofibrations and fibrations is to I mean the axioms of a model category are such that those capture abstract properties of cofibrations and fibrations. Okay, so the main purpose of introducing them, cofibrations and fibrations, the main reason is to factorize morphisms. Very roughly speaking, this is like a blasphemy statement that I am making right now, but the very rough intuition behind talking about cofibrations is so that you think of some nice monomorphisms and think of fibrations as some nice epimorphisms, that's all. And the reason for introducing weak equivalences is to capture, is to abstractly capture what homotopy equivalences are. The idea is again to, so one of the reasons for introducing model categories was to perform localizations again. And as you saw in the case of, let's say, chain complexes, you localize at quasi-isomorphisms. Here you use the weak equivalences for localization. That's all. I won't say much more because I myself will get confused, and I will confuse you more. But so, very roughly speaking, think of model category theory as a framework for doing some abstract homotopy theory. That's all. There is a more general notion of a homotopy, I mean, categories which support homotopy theory. Those are called homotopical categories. And model categories, I mean, the weak equivalences, if you look at the weak equivalences, the weak equivalences considered as subcategories of your, I mean, the class of all weak equivalent, instead of saying you have a class of weak equivalences, you can also say that you have a subcategory of weak equivalences. The subcategory of weak equivalences actually satisfies properties of a homotopical category. So a model category is again a refined version of a homotopical category. You can talk about a homotopy theory. Model categories have a framework to talk about abstract homotopy theory. That's all. I won't say much more. Yeah, you can talk about homotopy categories or model categories. Okay, you can, yeah. So it seems that he has already introduced what cylinder objects are. So that means he has already also introduced what left homotopy and right homotopy is. And then he has probably introduced what
Yes.
homotopies are actually. So what is the abstract notion of a homotopy in this context? So we won't get into all these things. These are non-examinable. Uh, he has also talked about the small object argument. Okay, fine. But that is again non-examinable. But I'm sure you have already seen what is the purpose of the small object argument. It's just to get nice factorization systems. I mean that's one of the purposes again. Yeah, so I'm sorry. We won't talk about all those things. We'll only stick to what we wanted to do this week. But since a question was asked what nerve of a category is and what is exactly the concept, let me just talk about this simple thing. So did he introduce simplicial sets? Do you remember?
Yes.
So a simplicial set, okay, before that we need this category. So consider so the objects of delta are
Natural numbers.
yes. So objects are box n, where n is a natural number. What does box n mean? Box n is actually this set. Sorry. When I say natural numbers, 0 is included. So box 0, box 1, box 2 and so on up to n. These are the objects of your category. Think of this as a partially ordered set. So let's say this with less than equal to. Morphisms are what are the morphisms? Those are non-decreasing functions. Composition is usual composition of functions, and identities are usual identities. So this is our category delta. I mean, this is sometimes called the simplicial indexing category or the simplex category, and it actually has many nice interesting properties. We won't mention any of them, but it has many nice interesting properties. One of them is actually the fact that delta has a monoidal structure itself. It's a monoidal category. It's a symmetric monoidal category actually. Is it a symmetric? One second. Yes, it is a symmetric monoidal category, and interesting thing is that if you take an arbitrary monoidal category together with a monoid object in it, then there will exist a unique functor from delta to your arbitrary category, which takes your so the monadal structure that I am talking about here is addition actually, and with respect to this monadal structure, box 1 has a what should I say, box 1 has a is a monad with respect to this monadal structure. So given any arbitrary monadal category together with a monad object inside it, there exists a unique functor from delta to that arbitrary monadal category, unique monadal functor which takes box 1 to your monad object in your arbitrary category. So this is like a universal property for your category delta. Besides this, there are other perspectives or other properties of delta as well. Now why is delta important? Because so that we can talk about simplicial sets. So a simplicial set, or rather a simplicial object in a category. So let's just talk about sets. So a simplicial set is a, what is it?
It's a functor from delta to set.
No, it's a functor from delta up to set. Let me just put my laptop on charge. 1 second. Yeah, so a simplicial set is a functor from delta op to set. In other words, it's a presheaf on delta. Oops, we have already crossed a lot of time. Yeah. So a simplicial set is a presheaf on delta. In other words, it's a functor from delta up to set, and so the main purpose for saying all this was to introduce the nerve of a category. So nerve of a category nerve of a category is a simplicial set. So how is it actually defined? So you take a category C. Do you know the definition of the nerve of a category? So a category.
No, I forgot.
Okay, so you take a arbitrary category C. The nerve of a category is this simplicial set. So how is it defined? So nerve of C should be a functor from delta op to set. It sends box N to the functors, the set of functors from box N to C. So do we know what this means? Or why, so we are referring to box N as a as a category first of all. Why? Because box N was a partially ordered set. It has an underlying category, therefore. If you remember the usual construction. So take any partially ordered set, construct your category as follows. You take, the objects of your category are the elements of the partially ordered set, and there is an arrow from an object X to an object Y if X is less than equal to Y. So that makes box N into a category itself, and hence we can talk about a functor from box N to C. What is this exactly? What is a functor from box N to C? It's just a sequence of composable arrows in C, that's all. So the set of functors from box N to C is exactly the set of all sequences of composable arrows, where the sequence of arrows has length n. That's all. And of course this NC is obviously a functor. You know how to define, you understand how to define this functor or extend it to morphisms. In other words, this construction box N getting mapped to func box n comma c is functorial. You know how to extend it to morphisms as well. This NC is a simplicial set. This simplicial set is called the nerve of a category, and as it turns out, it's something called an infinity category actually. I mean, we haven't introduced or defined what an infinity category is. An infinity category is again a simplicial set, but a nice enough simplicial set. It turns out that nerves of categories have this nice property of so that it qualifies to be called infinity category. This is the construction of the nerve of a category, and alternately you can also say that the nerve of a category, I mean, alternately you can also write this. This is equal to coproduct A0 AN in OBC CA0 comma A1 cross dot 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 cross CAN minus 1 comma AN. Exactly the same thing. Why did we actually talk about nerve of a category? Because I don't find any purpose anymore. Why were we talking about?
Because you were talking about adjoining an infinity category to any
Oh yeah,
category.
yeah. I mean, this is not exactly. I mean, this is one of the ways to think of to associate a infinity category to a category. Whenever people say associated infinity category, they don't usually mean just the nerve of a category. There is something more that people want, which is so there is some sort of a localization process also happening. Yeah, forget. We are not supposed to say all these things. You can Google Duskin nerve if you want. That is where the answer lies. Yeah, so let's just say ignore. Yeah, anyways, let's quickly see if we can solve 5 problems in 1 hour. I hope that the notation was clear for the lifting property. This is the notation we are going to use throughout. I hope that this notation is clear. Let's just quickly move on to solving problems. Otherwise, I am messing up a lot. Okay, so this is again the notation that was introduced. We'll quickly again see what this is. So C is a category, S is a class of arrows of C. We write S with a square on the top together with a diagonal to mean or refer to the class of all those arrows of your category which have the right lifting property against every arrow in S. And we write this notation. So first you write the square with a diagonal filler and then S to mean the class of all arrows of your category which have the left lifting property against every morphism in S. So these two notations are understood. Now let's focus on the problem. So problem 1a says that show that in the category set, if you look at, so 0 here is is the initial object which is the empty set. 1 here is the terminal object which is the singleton. So 0 to 1 there is supposed to be a unique map because 0 is an initial object or because 1 is a terminal object. So take that unique map. Consider this singleton class. So you have a class of arrows and this class has exactly one arrow which is this unique map. Now look at this. So look at this. In other words, what we are interested in is the class of all arrows which have the right lifting property against every morphism in this class, and there is exactly one morphism in this class. So we are talking about the class of all arrows which have the right lifting property against this unique morphism 0 to 1. What the problem is asking you to show is that this class is exactly the class of all epimorphisms in set. We know what epimorphisms in set exactly are, right? What are they?
Onto maps.
Onto maps. So we just want to show that the class of all epimorphism is in set are,
So
yeah,
if we take two sets X and Y and one morphism F,
okay,
I mean, if you draw the square, yes, X and Y and F, and there is a morphism from 0 to X.
we take an arbitrary morphism from 0 to x, but 0 is initial, so there is exactly 1.
So
Yeah,
yes, yes, and you can also take morphisms from 1 to Y, which will be the elements of Y.
okay. So take an arbitrary morphism, let's say V. So V actually is an element of Y. Yeah,
Now you are telling me to show that if is AP,
yeah.
right? Oh, there is a lift. You should draw the lift also.
Okay. So let F be here. We want to show first that F is an AP. So there is a lift. By definition of this class, we know this there is a lift to this problem. Let's call this lift H. Now,
Yes.
so
Now
so there is one
the
thing that,
triangles
so there
commute.
is one small thing that you missed here, which is whenever we talk about or ask about lifts, or whenever we say that something has a lift lifting property with respect to something, we always ask for this square to commute, right?
Oh yes, yes.
Provided this square commutes, then we can say that or talk about a solution of this problem, right? Yeah. So does this square actually commute? Does this square commute? This is easy.
No, no.
Why not?
Wait, wait. Oh, sorry. 0 is the phi, right?
Yes.
Oh yes, it will commute.
So it obviously commutes because 0 is initial object, right? There is
Yes,
exactly
yes.
one morphism from 0 to y. So since 0 is initial in set, there exists a unique arrow, unique morphism from 0 to y, right? So the square commutes. That means it has a lift. Now how do you show f is a epimorphism? So yeah, you tell, you say. So we have actually said a
So
lot.
now,
Yeah,
now you can draw the lift now.
okay,
So H is a lift.
yeah,
Then then FH is V, right?
yes. So note that
Uh, yeah,
regardless of whatever v you take, the square always commutes, right?
right.
And v is supposed to capture elements of y. So take an so we should rather
Yeah.
instead of drawing the arrows first, we should first start with an arbitrary element in y and show that there is an x getting mapped to that under f. So let's write it properly. So let f from x to y belong to this. We claim that f is an AP, is a surjection actually. So take some little y in capital Y and consider the unique map y from 1 to y with image. One is a singleton. So its image has exactly one element. We are denoting the unique map from 1 to y with image little y by y again. So we are sort of abusing notation here. Okay. So now we form this square first. We have this square where this v is actually y, and since 0 in set is initial, there exists a unique morphism from 0 to y, which means that regardless of whatever little y arrow we have taken, the square always commutes. So since f has the left lifting property against this unique morphism from 0 to 1, so a lift will exist. So a lift exists by definition of f. And now can we say that we are done?
Yes, yes.
Because the bottom triangle commutes, since f composed h is equal to y. And what is h? H is just an element of x. So f of h of star, where star is we haven't written this. Star is the unique element of 1. Okay, so let's say, so f maps h thought of as an element of x to y, and we are done. Let's say this is little x. Okay, so this one side is proved. We have proved that any f belonging to this class is actually an epimorphism. Can we prove the converse? Conversely, assume let f be an ap. Can we prove that f has the left lifting property, right lifting property against the unique morphism 0 to 1? So 0 to 1, x to y, f. We take an arbitrary arrow here. There is only one. We take an arbitrary arrow here.
This will commute.
This will commute. I mean, we shouldn't say this will commute. We should assume that this commutes, right? I mean, it commutes anyway, but we should assume that this commutes, because we want to show that f has a left lifting property against the morphism 0 to 1, which means that we should start with a commutative square like this and show that this square can be completed using a diagonal. So conversely, let f be an AP and take any commutative square. So since this anyway commutes for any arrows 0 to x and 1 to y, I'll put commutative in brackets. So we take any commutative square like this. Why does a lift exist? Yeah, okay. Why does a lift exist to this? Because if is okay, so let's use some names. So let's say this is v, let's say this is u. Because f is an epimorphism, that is a surjection, so there exists some little x in capital X such that f of x is equal to v. Again, we are abusing notation. We are thinking of v, which is this map from 1 to y, as some element of y. That is why we are writing fx equal to v. So x is an element in capital X. We can take the corresponding arrow little x from 1 to capital X, which corresponds to little x, or whose image is exactly little x. and this arrow will actually make both triangles commute. This upper triangle will commute obviously because, again, because 0 is initial, so any two maps from 0 to x are the same, are supposed to be equal, because what is the definition of an initial object? An initial object is an object such that given any arbitrary object there is a unique arrow from 0 to that an arbitrary object, right? And this bottom triangle also commutes precisely because f of x is equal to v. So note that here the solution, this is just a solution to a lifting problem, because since f is a surjection, right, you can take any arbitrary element v in your codomain. F is a surjection, I mean, you can look at the fiber of your map over that element in your codomain, and there can be many elements. In other words, there can be many little x which get mapped onto v. Any such little x is a solution to this lifting problem. So I mean, f is not orthogonal to the unique arrow from 0 to 1. That is what I am trying to say. F has the right lifting property against the unique arrow from 0 to 1, but it is not orthogonal. Okay.
Yes.
Okay, so this solves the problem. So a lift exists. And this proves the converse as well. How do we prove part B? So what is part B? Part B says, again take 1. 1 is the terminal object, that is a singleton. There is a unique arrow from 1 coproduct 1 to 1, right? Because 1 is terminal. So what you do is you again take a singleton class consisting of exactly this arrow and look at the class of all arrows which have the right lifting property against this unique morphism from 1 coproduct 1 to 1. We want to show that that particular class is the class of all monomorphisms in set. So let's say let G or let's say let F belong to this class. Yeah, how do we show that F is a mono? So F has the right lifting property against this arrow. The domain of F is X and the codomain of F is Y. We didn't mention that explicitly, but yeah.
Yeah, now you finish the square.
Okay, so before we finish the square, since we want to prove that F is a mono, right, let's just do it in the, let's just focus on proving that F is a mono. So let's keep this square aside for some time being. So what are monomorphisms in set? They are precisely injections. So we want to show that F is an injection, right? Yeah, it's better that we write the domain codomain explicitly. F from X to Y. Yeah, so let x prime be in capital X with f of x is equal to f of x prime. Yeah, now tell me. Yeah, so we need to take two arrows, one coproduct 1 to x and 1 to y. What is the arrow from 1 coproduct 1 to x?
Is the tuple of, so I have a map from 1 to x,
Which is?
and you take the tuple, which is the unique map. Sorry, which is not a unique map, which is the elements of x.
Yeah, so you have a map from 1 to x which is little x. You have another map from 1 to x which is little x prime, which means that this pair x comma x prime of maps actually induces a unique map from 1 coproduct 1 to x, right? Yeah. So that if you take one
just
here,
using two elements of,
so we are using the universal property of the coproduct, right? So this is little x, this is little x prime. This induces a unique map from one coproduct 1 to capital X such that if this is your inclusion, I shouldn't say inclusion, if this is the structure map of the coproduct in the first component, or co-projection in the first component and co-projection in the second component, both triangles commute for this unique map from one coproduct 1 to X. We are denoting that unique map by x comma x prime. That's all.
Yes.
Yeah.
So it's just choosing two elements of x.
Yeah. So we have already taken these two elements x prime, right? And we have assumed that f of x is fx prime. We want to show that x is equal to x prime. So that is what we are doing. So I'll write this in details inside. How are we getting this map x comma x prime? So using the universal property of the coproduct, that's all. There is a unique map from this to this, which we are writing x comma x prime. So that if this is I1, which means the I mean this dot goes to the dot in the first summand, and this unique element goes to the dot in the second summand under this map. This both this two commute. Okay.
Yes.
Yeah. And what should we take for this one? For the map 1 to y?
So you take fx.
Yeah.
Or fx prime. They are same.
So fx equal to fx prime. So we are always abusing notation here. We are thinking of, we know that the identity functor on set is representable. It's represented by the object, the singleton set in the category of sets. So this means that there is a natural isomorphism from I mean the identity functor to the representable functor from represented by 1. So I on set to set 1 comma gap, right? There is a isomorphism I on set to set 1 comma gap, which means that you have an isomorphism from every set S. For every set S you have an isomorphism S to set 1S which is natural in the variable S. That is what we are doing here. We are abusing notation. We are identifying elements of S with maps 1 to S. Yeah. So we have taken these two maps. The question is, does this square commute?
Yes, it's commuting.
It's obviously commuting. The above square commutes. Obviously. Which means that there is a lift. So there exists a lift x double prime, let's say, from 1 to x, which is again just an element of capital X, such that the two triangles commute. Yeah. So, are we done? Sorry. Are we done?
So we need to show that x is equal to x prime.
Yes. Since the upper triangle commutes.
Yes. So x prime and x double prime, those are same.
Yes. X is equal to x double prime equal to x prime. That's all. So F is injective. And what about the converse direction? If F is injective, does it have the right lifting property against this unique arrow? Conversely, assume that F is injective. So you take one coproduct 1 to 1, the unique arrow, x to y, f. You take an arbitrary arrow u, you can take an arbitrary arrow v. So take a commutative square. Take a commutative square like this. We want to show that there is a solution to this problem. How do you show this? Saying that this square commutes, what does that mean? So let's say, since this is one coproduct 1, let's say the object in the first summand 1 is let's say dot, and the object in the second summand 1, let's say, is star. Okay, so saying that this square commutes exactly means that f of u, f of dot is equal to v considered as an element in y, and f of star is again equal to v considered as an element in y, because this entire square commutes, right? We can agree?
Yes.
What does a unique map from one coproduct 1 to 1 do? It sends dot to the unique element of 1, it sends star to the same unique element of 1. So when you apply v, you just, in both cases you get v only. That is what I am trying to say. Since f is injective, that is a monomorphism in set, dot is equal to star, right? I'm very sorry. This doesn't make sense. I mean, what I'm saying is, if not f of dot, f of u of dot is equal to v, and f of u of star is equal to v. Yeah. So since f is injective, u of dot is equal to u of star. Take the corresponding map. 1 to x, which is u of dot is equal to u of star, that common element. Take this corresponding map and check that that will be a lift. That will obviously be a lift. U of dot equal to u of star. This is a lift. This is a solution to our lifting problem. So f belongs to one coproduct 1 to 1, yeah. So this proves the converse direction. Any questions?
No.
Okay.
It's a beautiful problem.
Thanks. So problem 2. Okay. So consider an adjunction. So you have category C and D. You consider an adjunction. There is a functor F, which is the left adjoint. There is a functor G, which is the right adjoint. So let L be a subset of C, rather a class of morphisms of C, and R be a class of morphisms of D. What we want to show is the following, that F applied on L, which is now a class of morphisms of R, is contained in this if and only if L of this contains G of R. So again, we know what these notations mean, right? This is the class of all morphisms of D, which have the left lifting property against every morphism in R, and this is the class of all morphisms of C, which have the right lifting property against every morphism in L. We want to show that this will hold if and only if this will hold. In other words, we want to show that every morphism in FL has the left lifting property against every morphism in R if and only if every morphism in GR has the right lifting property against every morphism in L.
So we can
I'm
start
here
with
only. You
FL
can,
subset.
yeah. I'm here only. You can say what you want to say.
Yes, I'm saying let's start with the left side one. Hello.
Yeah, sorry. We start with the left side one. So take FL. So assume FL is contained in this. Okay. Now what?
Yes. Should we write this in like in sets? I mean in the language.
Okay. So
So you can take an element of L.
okay. So so for all L in L, FL. I mean this holds for every R in R. Yeah.
Yes, that means we can draw a square.
Okay. So um okay.
If FL in the left and R in right.
Okay. So it's better if we write the source and target. So L, let's say this is in C, right? So A to B, let's say A to A prime, let's say. Oops. Yeah. So this object is FA. This object is FA prime. This is FL. Yeah. And take an arbitrary R, let's say B to B prime. This is R. Okay.
Yeah. So it has a left lifting property. That means we have a commutative square here, right?
No, we should start with a commutative square and then we have a left lifting property.
Oh yeah, sorry. So there is a commutative square here.
So take any commutative square in other words, take any arrow in the arrow category like this. So an arrow will be just a pair of arrows making this commute. If this commutes, then there is a lift. Right?
Yes.
So rather,
Yes.
we shouldn't say this. We should rather start with the other one. I mean, we assume, as you said, we are assuming the first one. We have assumed that FL is contained in this box R. We want to show L box contains GR. So want to show L box contains GR. So take any R. Take R in R from, let's say, B to B prime in R. Let L from A to A prime. So let's not write this here. For all in, let's say for all in inland we have this. Yeah. So let L from A to A prime in L. Yeah. So now we want to show G of R is contained in L box, which means that we have A prime, this is L. We have G of B here. We have G of B prime here. G of R here. In everything is happening in C. We take an arbitrary arrow U. We take an arbitrary arrow V. We want to and assume. So suppose we have a commutative square. we want to show that a lift exists. Suppose we have a commutative square like this in C for some arbitrary arrow u and some arbitrary arrow v. Yeah. How do you show now that a lift exists? Did you understand what I'm saying?
Yes.
Yeah. Now how do you show?
Should we apply if on the right?
Should we apply f on the right, or can we use our, I mean, you want to you are saying we should use our adjunction, right? That is what you are saying.
Yes, yes.
So using the adjunction, we have a square. So fa prime, fl, b prime, r, fa prime to b prime. What is this? This is v bar, let's say, and what is this? This is u bar. What are u bar and v bar? So we have an adjunction, which means that d of f of a comma b is the same, is in bijection with c of a comma gb. D of fa prime comma b prime is in bijection with c of a prime comma gb prime. D of fa prime comma b prime is in bijection with c of a prime comma gb prime, right? So from a to gb you have u, we are denoting the corresponding element here by u bar. You have v here, we are denoting the corresponding element by v bar. This is the notation that we are using. Yeah, my question is, does this new square commute? What do you think?
It should.
Why? Why should this new square commute? Why should this new square commute? Because of the, in one word, because we have an adjunction, right?
Yes.
Because of the naturality of the adjunction, this commutes, right?
Yeah.
We have a commutative square. So what does the naturality of the adjunction mean? Then, so when we say that,
So we have changed the A and B.
yes, exactly.
Since
Using maps, we have changed. So what does the naturality of an adjunction mean? I mean, what does the naturality mean for an adjunction? So this means exactly that if you take A here, I mean, sorry, if you take C here, if you take D here, and if you take, let's say A here, let's say A prime here, if you take an I'm sorry, how should I say this? Yeah, you take A here, you take sorry, FA here, you take B here, you take GB here. This is category, so this is happening in the category C. Sorry, I'm a bit messed up today. This is happening in the category C, this is happening in the category D. right? What does having an adjunction mean? It means maps from FA to B are the same as maps from A to GB. And what does, I mean, that is not all for the definition of an adjunction. The important thing is the naturality in the definition of an adjunction. What does naturality mean? It means if you change A by A prime, let's say, with by using an arrow, let's say, so let's say this is F, this is F bar, let's say, this is U. So from FA prime to FA you have FU. Let's say you change B by B prime as well. Let's say this is V. So GB to GB prime you have GV. So what you have is a map from A prime to GB prime in C, and what you have is a map from FA prime to B prime in D. Now since there was an adjunction, this means that maps from A prime to GB prime should also be in bijective correspondence from maps from FA prime to B prime, right? Say the naturality exactly means that under that bijective correspondence, the arrow GV composed F bar composed U corresponds to under that bijection corresponds to the arrow V composed F composed FE. This is exactly what the naturality means, right?
Yes.
And that is how you get a commutative square using naturality of an adjunction. So I always say this, that so whenever you refer to whenever you say that you have an adjunction, it's not exactly the bijection that is really, I mean, that is important, of course that is important, the bijection of Hom sets is important, but what is more important is that you have a natural bijection. The word natural here is more important. So using the naturality of an adjunction, we have a commutative square like this. So this is just recalling the naturality. Also to the viewers, this is not so, I mean, we probably have used different notations here than were used here, so don't mix them up. This is just recall the naturality of an adjunction exactly means this. The bijection is in a sense very coherent with compositions in both categories. Right. So you can check that using exactly this, this is what naturality means. Using this you can check that this square commutes. And since R, I mean since this holds, so this and this square commutes, so we have a lift. Since f of L is contained in this, there is a lift. So what do we have? So FA to FA prime, FL, B to B prime, R, FA prime to B prime, I'm sorry, V bar, FA to B U bar. A lift will exist, let's say H, making both triangles commute. But this is not what we wanted, right? We wanted a lift for this one, right? Do we get a map from A prime to GB if we have a map from FA prime to B?
Yes.
We
by
have.
the adjunction.
Yes. Under the natural bijection, script D FA prime comma B to script C A prime comma GB, take the corresponding arrow arrow, take the morphism h hat, let's say, from a prime to gb, corresponding to the morphism h from fa prime to b. So we have a prime, I mean sorry, a prime, b, b prime, I'm sorry, gb prime, this is v, this is u, this is what is this, this is l, this is gr,
L.
yeah, and we have an h hat here. Check that h hat is a lift. And why will it be a lift in one line or in one word? Because h here was a lift making both triangles commute. H hat should make both triangles commute here as well. And why is that? Because again, because of the naturality, right?
Yes.
Using the naturality of an adjunction. And converse follows by duality. So the converse follows by duality. So when I say the converse, I mean this. So we have shown that this implies this. The converse is this direction. That follows by duality. Any questions?
No.
Okay.
So is this saying that when we have adjunctions,
Yeah.
this factorization system behaves well?
With respect to adjunctions, yeah. In fact, you can prove something very interesting, and you can try to show this. You can. So let's say I'll put this in red. In fact, for people interested in order theory like Prannoy, in fact, you can prove that. I shouldn't say in fact, actually. You can, in fact, you can prove this statement that. So what you do is you look at. So uh, take a category C. Let's say that your category is has some size restrictions. I mean, some kind of probably locally small won't work. Smallness will work. But yeah, I mean, those things don't matter as long as you have fixed your universe and fixed your set theory. So take any category C. Let omega be the class of all. Okay, so let omega equal to 2 to the power mod C. So what does mod C mean? The class of all morphisms of C. So omega is the class of all, is a power set of mod C. Every element of omega is a collection of morphisms of C. Okay, so what you have is two operators now from omega to omega. And in fact, yeah, I should say something more. Omega comma this is a partially ordered set. Set. So what we defined today was two operators, right? One is this operator and one is this operator, right? Okay, it hasn't come yet. Well, let's wait. Yeah, we have these two operators, right?
Yeah.
You can show that And what is the interesting thing about both operators? I mean, this. I mean, what can you say? If let's say if A is a class of morphisms which is contained in B, what can we say about this and this? Which one is contained in the other? In which one?
Should reverse the arrows.
Should it? Okay, so tell me. So think. Should the arrows be reversed? So if A is contained in B, which one is contained in which one? So suppose you take some F here. Let's not put anything. Suppose you take F here, which means that F has the right lifting property against every arrow in A, right?
Yes.
Okay, yeah. So I should say, suppose you take F here. I'm sorry. Suppose you take F in B box, not A box. I don't know why this writing lags. I have already written these things, but it doesn't sort of show up on the screen. Uh, let's just wait. Suppose F is in B box, yeah. That means F has the right lifting property against every arrow in B, right?
Yes. Then F is in A.
Then F is in A box. So this implies F is
Yeah,
in A box. So should the inclusion be reversed? The inclusion reverses, right?
Yes.
Yeah. And similarly, the other operator also does the same. So check that. You can check that these two operators.
Galois connection.
Yes, these two operators form a Galois connection. We have seen this in Galois theory previous. I mean, not we, but this happens in Galois theory, in the theory of covering spaces, etc., etc. And I'm sure he has introduced what Galois connections are. Those are just adjunctions for partially ordered sets. So to be precise, you can write an op here. Okay. Any questions?
No.
So since we are talking about partially ordered sets, you can ignore categories, ignore op as well. But the correct thing is to write an op there. Okay, let's quickly move on. So let A be an abelian cat. Okay, we are now again coming back to.
Is this the last problem?
This is the third problem. We have two more problems.
Okay.
Okay. So what I do is, if we can't solve problems quickly, what I do is, if we can't solve problems quick. Oops, I'm sorry. Yeah, if we can't solve problems in time, what I do is, I generally oh god, if we can't solve problems in time, I generally give them as assignments or exercises. Yeah, so let A be an abelian category. Let A be an abelian category. We take a projective object P in OBA. We want to show that P is a generator if and only if this is non-trivial. I believe this statement was mentioned sometime in the lectures, but we want to show this explicitly now. So we know what a projective object is, right?
Yes.
And we know what a generator is.
Yeah.
Okay. So we want
to
to
recall the definition.
Okay, sure.
In short.
Okay. So object P in OBA is called a projective object if A of P comma gap is
the generator.
Okay. First of all,
okay. This preserves epimorphisms.
Yeah, for abelian categories this means it is exact.
Exact.
And an object G is called a generator if this functor is a faithful functor. Okay. In other words, what saying that
Yeah.
G is a generator means that if you take a non-zero morphism, we are in the additive category pre-additive category context, so we can, instead of taking two different morphisms, we can take a non-zero morphism A to B. There is a morphism G to A such that this composition is also non-zero. This is what a generator means. Okay. Yeah, so if P in OBA is projective, we need to show that P is a generator if and only if APA is non-zero for all A in non-zero. How do we show this? So assume first, let let P in OBA is a projective generator. How do we show that this thing is non-zero?
Which one? P.
I mean this, for every A non-zero, how do you show that this Hom set is non-zero? Let A be a non-zero object in A. We claim or want to show that this Hom set or Hom group is non-zero, which means we want to produce a non-zero morphism from P to A.
Yes.
How do you do this?
Then we can consider its kernel.
Whose kernel? We don't have a morphism yet, right?
Oh, sorry.
Do we have, first of all, can we just talk about one non-zero morphism regardless of whether it is from P or from something else, doesn't matter. Can we talk about some canonical morphism here for an object A?
Non-zero you mean?
Non-zero morphism for the object A. So A has been assumed to be not the zero object. What does that mean? Or what can we say about the identity morphism of A?
Oh, it's a epimorphism.
No, that's always true, right? The identity morphism is always an epimorphism. It is an isomorphism. But since A is non-zero, in your category A, in your abelian category A, the identity morphism is also non-zero, right? We know that zero objects have this characterization, right? An object is zero if and only if its identity morphism is a zero morphism, right? That's a very powerful characterization. So since A is non-zero in A, the identity morphism A to A, 1A is non-zero, right? Now P has been assumed to be a generator. So there exists a morphism P to A, right? Such that P to A to 1 to A 1A, this composition is non-zero, right? Because P is a generator. Because P is a generator. Now what is this composition? This is just equal to the arrow P to A. This is equal to the arrow P to A, right? So we have a non-zero arrow therefore from P to A. So the Hom group is non-zero. Done. What did we not use here? We didn't use a property of P here, right?
Mm.
the
Right.
projectiveness. Now conversely, let this be non-zero for every a not equal to 0 in A. Can we conclude that P will be a projective generator?
Is P projective given, right?
P is projective, yeah.
Okay. So if we take the identity map from A to A,
No, we are given this, right? We don't know what A is. We know that this holds for every A. We want to show that P is a generator, right? So we should not start with the identity map from A to A, right? We should start with any non-zero morphism from A to B, right?
sorry, yes.
Yes, right? So conversely, let this hold. So want to show P is a generator. We know P is projective, that is given to us. So let A to B be a non-zero morphism, F, let's say. Yeah. So take a non-zero morphism A to B.
And we have that morphism. We have a non-zero morphism from P to A also.
B to A.
P to A.
Why?
Isn't that the hypothesis?
No, we that is not the hypothesis, right? The hypothesis is that this. Oh, okay, okay. Yeah, yeah, yeah. Sorry, yeah. We have. Okay, so let's first. So we have a non-zero morphism P to A, right? Okay.
So we need to show that composition is non-zero.
Yeah, but will that always be true for any arbitrary morphism P to A? That won't be true in general, right? It could happen that the image of P is in the kernel of F, right?
Mm.
So what do we do? So I'll write down the argument quickly. Since we are in an abelian category, we know we have a factorization system AP mono, right?
Yeah.
So what we do is we take a factorization of F, or since this will be unique, we take the factorization of F. So this is image of F, and this is some mono. So we have this fact. Let's say this is E. Let's say this is M. F can be factored in this way. Now this arrow is an AP. The image arrow. Okay, sorry. This is not actually the image. This is rather should be called the co-image arrow. But okay, anyways, this arrow is an AP, right? P is projective, right? What does that mean?
So we have a map from P to A, and there is a lift of E.
Yeah, yeah. So we have this alternate definition of a projective object was probably not mentioned explicitly, or it might have been in the lectures. But the idea is that maps from P to something can be lifted along AP morphisms. That is also a equivalent characterization of projective objects, right?
Yes.
So what map from P to image of F should we take?
it should be the composition of E and the morphism from P2.
No, that is what I'm saying. We are not fixing any morphism from P to A priori, right? Because
Oh, okay.
taking an arbitrary morphism, it could happen F composed with that is 0. So what is the idea? The idea is we should take a morphism from P to A, but what morphism? We should take such a morphism from P to A whose image is not contained in the kernel, right? Now, what does the
Yes.
first isomorphism theorem for an abelian category say? It says that the kernel of the co-kernel of an arrow is the isomorphic to the co-kernel of the kernel of that arrow, right? In other words, what it says is that A over kernel of F is isomorphic to image of F, right? For an abelian category. So when you take a quotient, so why are we all of a sudden considering image of F here? Because what is image of F? It's the quotient of A by the kernel of F. So the kernel gets reduced to 0, right? Essentially. So now taking a non-zero arrow from P to image of F, because P has this property that this holds for every non-zero object A, there is a non-zero arrow from P to image of F, right? And taking a non-zero arrow essentially means that, I mean, if you lift it upwards, that would give you some arrow whose image is not contained in the kernel of F, and then the composition will be non-zero. That is what the idea is. So we wanted an arrow from P to A, but such an arrow whose image is not contained in the kernel of F. And this construction actually does the job. We have reduced, what we do is we essentially crush the kernel. That is why we are taking the image all of a sudden. Right? So since F is non-zero, image of F is non-zero. So there exists a non-zero arrow by our hypothesis. There is a non-zero morphism P2 image of F. Right? We take this non-zero morphism P2 image of F. Since P is projective, there exists an arrow P to A. Let's say G. Check that, and this is easy to see. Check that if compose G has to be non-zero. This will hold. Okay. So that is the idea. So the interesting thing here is that we have sort of externalized the notion of a projective generator using this criteria. So this is like an external definition. Why? Because we are using sets or other groups here. Instead of looking at the object intrinsically as an object in the category, we are rather looking at a Hom set or a Hom group. So we have externalized the definition of a projective generator. This is what the purpose, this is the purpose of the problem. Okay, problem B, if A is co-complete and has a projective generator, show that A has enough projectives. We know what enough projectives are, right? That was covered because projective resolutions were covered this week.
Yeah.
Okay, so suppose A is co-complete and has a projective generator. We want to show that A has enough projectives. I'll only give hints because we are running very late. If A is co-complete and has a projective generator, show that A has enough projectives.
So if the projective generator is P and A is any arbitrary object, we need an epimorphism from P to A, right?
Correct. So no, I mean, what does having enough projective means? It means that if you take an arbitrary object A, there should be some projective object together with an epimorphism. It need not be the case that this projective generator should have a map out of it into your arbitrary object. There could be some arbitrary projective object. So let P be a projective generator. Yeah. Let A be an arbitrary object. Let A in OBA. Yeah. How do we get an epimorphism from some projective object to A? So I'll again just give you this hint. So we are in an abelian category, which is in which, so therefore the Hom sets are abelian groups. It's a pre-additive category. Therefore the Hom sets are small. They are sets actually, which means that this is a set. So now what we can do is that we can take, since we are in a co-complete category, we can take the co-product of copies of P indexed over this. Okay, this co-product is exists because we have this co-product exists because we are in a co-complete category, and so this is a co-product of copies of P. It's sometimes also referred to as a co-power. It's a co-product of copies of P. And from this we have a map to A. What map exactly do we have a map? What map do we exactly have from this to A?
So for so P to A, there is a map, non-zero map, and we can take the sums, right?
Why do we need to take non-zero maps? We can take, because we are indexing over all maps, right?
Oh yes.
So there is a map, there is a morphism induced by the, so how are maps from coproducts induced? They are given, they are characterized exactly by maps from every individual summand. And what is a summand? It's a summand, I mean a summand is P, and the class of all summands is indexed by this Hom group or Hom set, right? So induced by the collection script A P comma A, or more explicitly this collection of maps from P to A, right? So the universal property of the coproduct gives you a unique map from this to this, making all the small triangles commute. So yeah, so the claim, or rather, okay, so this was an assignment problem. So check that. I have checked this. So check that this will be a projective object. In fact, in the assignment you are asked to show that a direct sum of projective objects is projective. You can actually show that a co-product of projective objects is projective. So check that this is projective, and check that, and that the morphism we are referring to above from the co-product of copies of P into A is an epimorphism. And that will do the job. Okay, I won't say much more, we don't have time, but you can check all these things. So this is very interesting. If P is a projective generator, then your category has enough projectives. In general, it is not true, not even for a Grothendieck category, that it has enough projectives. There are always some conditions needed for a Grothendieck category to have enough projectives, so that you can then talk about whatever you want to do. You can talk about projective resolutions, etc., etc. But interestingly, a Grothendieck category has enough injectives. So if you formulate the dual notion, right, of this of the notion of, so the dual notion of a projective object is that of an injective object, and the dual notion of that of a projective resolution is that of an injective resolution. So you can actually prove that a Grothendieck category has enough injectives, but this is not true. Having enough projectives is not always true. Not always. This doesn't always hold even for a Grothendieck category. Yeah. So quickly we'll solve this one. We'll solve the first part, leaving the second part as an exercise maybe. Okay, so let C be a category with finite limits. It's a Cartesian category, finitely complete category. And suppose you take a weak factorization system EM. We know what a weak factorization system is. E and M are classes of morphisms. Every morphism in your category can be factored as a morphism in E followed by a morphism in M. E is exactly the class of those morphisms having the left lifting property against every morphism in M. M is precisely the class of those morphisms having the right lifting property against every morphism in E. And for the two redundant conditions of closure under compositions and isomorphisms, etc. Subcategory condition. Yeah. Show that for a pair of morphisms with F a monomorphism, F composed G is in M implies G is in M. Okay, so EM is a factorization system. We quickly write what M is in terms of E. M is exactly E box. So we are given a pair of morphisms FG, and we are given that F is a monomorphism and the fact that F composed G is in M. We want to show that G is in M. How do we show this? So I wrote this for this precisely for this reason. So since M can be written, or M is exactly the class of morphisms having the right lifting property with respect to E. E is the, what do you say? E is the closure of, M is the closure of E under this operator box. The right one, the right lifting property one. So to show that some morphism is in M, it is enough to show that it has the right lifting property against every morphism in E. That is what this writing this exactly achieves. So what we want to show, so want to show G want to show for every morphism E in E, E G. We want to show this. G has the right lifting property against E. So let E from, okay, we don't need to write objects here. So take an arbitrary morphism E in E. This is E. And let's write F first, and then let's write G. What we want is, suppose we have a commutative square like this, right? Okay, yeah. This is G. Take a commutative square. Like this. This is U, this is V. We want to show that this has a lift. We want to show that there is an arrow from this to this H, making both triangles commute. How do you show this? We know that F oh, I'm sorry. I think this should be G, this should be F. Yeah. That's a mistake. Yeah. F comes later, G comes first. Yeah, so take this commutative square. We want to show that this has a lift. We have to use the fact that,
we draw the F also.
okay, you draw the F, I draw the F also. So we'll draw F. Yeah.
And and if you complete the commutative square, I mean,
So what arrow should we take from this object to this object?
I think we are talking about the bottom object of P.
Yeah, so oh no, I'm sorry. Yeah, I'm sorry. I'm sorry. What, yeah, what arrow should we take from this object to this object? Yeah.
We can consider the composition
Okay. So we
of
take
this
this
P.
arrow if composed V, and we take this arrow. What should this oh, we don't need to. Yeah. I'm sorry. This is enough. So take the square, take the commutative square. Square. So this is E, this is F composed V, this is G, and this is U. This square obviously commutes, right? What is F composed V composed E? What is this composition? This composition is this composition, right? Right?
Yes, yes.
Something is, oh yeah, sorry. F composed V.
F composed. Yeah.
Yeah, so F composed V composed E is exactly equal to F composed G composed U, because this square commutes. So we take this commutative square. Since F composed G is in M, right? Since F composed G is in M,
You say F is mono, right?
yeah, F is given to be mono.
Oh, then we can have a commutative square. Oh, the upper commutative square is given.
Yeah,
Oh,
that
yes.
was given, right? We just completed this. So let's keep this separated. Let's keep this separate. Yeah, this is V. We started with a commutative square, right? Because that is what lifting problem means.
Hmm.
We then extended A with F, and we formed this F composed V. We considered this commutative square now. Since F composed G is in M, there exists a lift H as indicated in the diagram, making both triangles commute. So if we draw the entire,
So if composed B composed H is F composed B.
sorry,
If composed G composed H is F composed B,
yes,
and F is mono, so you can cancel out.
yes, exactly. So what we have is a commutative diagram like this. So this is U, this is E, let's say this is G, this is F. We had this is F composed V, right? F composed V composed G is F composed G composed U. Yeah, so we have this H, right? And we know this is V, right? Right. So what property of H did we know for a priori? So since H is a lift, we know H composed E is equal to U. So this triangle automatically commutes, no doubt about that. What we want to show here is this triangle also commutes. G composed H is equal to V. This is what we want to show. What do we know about H? We know that F composed G composed H is F composed V. Now, what do we know about monomorphisms? F is a monomorphism, means it can be cancelled from the
Left.
yes. Momomorphism. monomorphism. Yeah. We have G composed H is equal to V. Done. So V. H is also a lift for this, for the square we started with. Done. Since E is arbitrary, so G is in M. So G has the right lifting property against every morphism in M. Done. Against every morphism in E. Done. And the second question asks you to show that M is also stable under pullbacks. I'll leave the. I'll complete this later, and you can try this by yourselves as well. So for now I'll just write 2 is left as an. Is it 2 or is it B? 2 is left as an assignment or exercise. So what does 2 say? 2 says that, so this is like one of those properties that follows from the fact that you have a weak factorization system. As I mentioned, weak factorization systems are really powerful. I mean, the assumption is really strong, which is why it is really sort of, sometimes it becomes very hard to find one, and that is perhaps achieved by the small object argument as well. So one of those properties is that if EM is a weak factorization system, M is stable under pullbacks. So when we say stable under pullbacks, what we mean is that if you take an arbitrary arrow in M, and if you take any arbitrary arrow H in your category, if you form this pullback square, note that we are in a category with finite limits, so pullbacks exist in particular. If you form this pullback square, if M is in M, that would mean that this pullback projection will also be in M. M prime is the pullback of M along H, so M prime will also be in M. This is what stability under pullbacks means. Stability of a class under pullbacks means. This one is really interesting, by the way. I mean, proving this is more interesting. So for now I'll just leave this as an exercise, and I'll quickly end with the last one. So you consider an adjunction Fg of functors of abelian categories. What you want to show is that if G is exact, the right adjoint functor G is exact, and P is a projective object of A, then Fp is a projective object of P. So what this says is that if you have an adjunction, okay, let me ask you this question. G is a right adjoint, right? And we are given, so my question is, what extra condition do you need to say to claim that G is exact? If G is right adjoint, it is already, I mean, automatically it is
right exact.
No, right adjoints are always left exact, because right
left
adjoints
exact,
preserve
yeah.
limits, right?
Yes, so it preserves co-limits also.
Yeah, and no, it preserves finite co-limits.
Yes,
So saying that G is exact, so to claim that G is exact, you need to say that G is right exact. That's enough, because it is automatically left exact. Okay, so what this problem says is that projective objects are preserved by left adjoints if the corresponding right adjoint is an exact functor. And this actually is a very powerful theorem in categorical algebra. So yeah, how do we show this quickly? We want to show Fp is projective. We are in the context of abelian categories. We can just show that the functor, so want to show that the functor B Fp bar is exact. is exact. So let 0 to b prime to b double prime to 0 be an exact sequence in B. By the way, for any Hom functor, can we say something? I mean, something is automatic, which I mean, one-sided exactness is automatic.
It preserves limits.
Preserves limits. So it should be
Left exact.
left exact. Yeah. So to show that this is right exact, it is enough to claim that it preserves epimorphisms, or more precisely enough to claim that it preserves co-kernels. So let this be an exact sequence. You have a question?
No, no.
Okay. So let this be an exact sequence in B. So what we actually want is to show that 0 to Hom functors are automatically additive, so no need to worry about that. I mean, preserve 0 objects in particular. I won't label the morphisms now, it's understood. So one, that this is exact. We want to show this. How do you show this? Keep in mind we had an adjunction. I'm here, just you can answer. Yeah. How do you show that this is exact?
Those sets are in bijection with. Should we use G?
Yes, of course. You are correct. These Homs are in bijection with, or rather in isomorphism of groups with.
Like P comma GP dash.
Correct. Yeah, actually I should also mention if is additive. But okay, I mean the idea should be correct. So the correct the full statement should be this. So show that if G is exact, if is additive. We use the additivity implicitly here actually. We don't use it explicitly. Yeah. So as Pranay is saying, we take this. If P comma B P comma B double prime to 0 to A of what is this?
P comma GP dash.
There is an isomorphism from this to this. There is an isomorphism from this to this. There is an isomorphism from this to this. Why does this commute?
By naturality
Of
the adjunctions.
yes. The square commutes. Not adjunctions, just one adjunction, right? There is only one adjunction here, right?
Yeah.
Yeah. So the square commutes by the naturality of the adjunction. The squares commute by the naturality of the adjunction. Right. And now what?
Yeah, and the lower row is exact.
The lower sequence is exact.
Yes,
And why is that so?
because G is exact.
Because G is exact and and what else? So G is exact means that this is exact. But why does the sequence of groups, why is the sequence of Hom groups exact? I mean, when you apply P comma gap, why is this still exact? Because
It's exact function.
no, Hom is not exact. Yeah, yeah. I mean, I mean, because
P is
P,
projective.
yes, exact. Because P is projective, Hom P, I mean, Hom P is exact, so this is exact. The sequence in this is exact as G is exact and P is projective. And what does this isomorphism do, or what does this isomorphism say? This is exactly an isomorphism of exact sequences. If you consider an auxiliary category of exact sequences, then this triple of arrows is exactly an isomorphism here. I mean, if you, I shouldn't be very precise. If you consider an auxiliary category of sequences like this, 0 to something to something to something to 0, then this is an isomorphism in that category, this triplet of maps.
Right.
So this will also be exact. And you can prove this explicitly. The exactness you can prove explicitly because you have isomorphisms. So the sequence script 0 to script b of fp comma b prime, I mean, to script b of fp comma b to script b of fp comma b double prime to 0 is exact. So fp is projective. Okay. Actually, I should
Yes.
say something more here. It's not just an adjunction that works. So consider an adjunction with the bijection. So there is a canonical bijection from a natural bijection from f a comma b to a of a comma gb, with the bijection being an isomorphism of groups. That is needed, right? We want these three maps to be not just bijections but isomorphisms, structure preserving maps, right? Then only the things about kernel and co-kernel get transported to this top sequence, right?
Yes.
So I should say with the bijection being an isomorphism of groups. Usually when people talk about categorical algebra, they always mean this kind of an adjunction. That is how adjoints are introduced in this in books or in papers, etc. So we have an with the adjunction being an isomorphism of groups. Okay.
What is a good reference for this subject? I mean, for
Always, I would
factorization
always
system.
recommend Weeble, and there's also one other excellent reference, which is so you
What do you say? I can't hear.
what?
What did you say? Which book?
Okay. So there's a reference for homological algebra, right? That is what you want.
Yes, and weak factorization systems, all
Okay.
these
So
things.
weak factorization systems, I don't know any book reference, but you can always. I mean, I learned it using the Stacks project website. Okay. Or you can also follow NCAT That is how though I learned those things online. So I can give you a book reference, two book references for homological algebra. One is Weeble. I'm sure you have heard of it.
Yeah, yeah.
Charles Weeble, and second one is Lang's algebra. This one is very nice. It has a lot of homological algebra. This is like a dictionary book. This is like Dummit Foot. But this, I mean, if you want to learn it faster, Lang is probably the best one. But you can also definitely you should try this one as well. It has everything. It has horseshoe lemma, comparison theorems, all of those things. Okay.
Okay, okay.
Any other questions?
No, thank you.
Yeah. Okay. I'll stop the recording then and see you next week. The last week will be perhaps the most interesting one because we will be talking about
Yeah,
Foucault's theory. And yeah,
focus.
so let's meet next week. I'll stop the recording.
Okay.